Welcome back, everyone. Thanks for coming. In this series of lectures, I've been talking about measures of association, ways to link risk factors to the outcome, hopefully reflecting the impact, the causal effect of some risk factor on some outcome. And we've talked about some of the basic measures of association, risk ratios, odds ratios, rate differences. Well, now I'd like to give you an alternative, a variation on one of those measures of association. It's called the number needed to treat. It's a measure of association you might see in clinical epidemiology research. And to explain it and to present it to you, I'd like to use an example done by one of my colleagues here at the Harvard School of Public Health by the name of Paul Ridker. Well, this was the results of a large randomized clinical trial. Now, we'll talk about that type of study design in a few weeks, but all I'm going to do today is just show you the results of that study to use it as an example to explain the notion of number needed to treat. Well, this study involved a large number of people who were randomized either to receive a drug, a statin drug, or to receive a placebo. 8,901 people were randomized to receive the statin, and during the time of follow-up, 198 of them died. So what's the estimated risk? What's the cumulative incidence of death among the people randomized to receive a statin? Well, it would be 198 divided by 8,901, which is this 0.2222. 2% of them died. Alternatively, those who were randomized to receive a placebo drug, and we'll explain in a couple of weeks what a placebo drug is and the basics for randomized trials at that time, but they had a different 8,901 people, and 247 of them died. And that gave an estimated risk of death, a cumulative incidence of 0.0277. Well, let's use these data to answer a couple of questions. Suppose you had 1,000 people and they were treated with that statin drug. How many would you expect to die? Well, if I go back to the previous slide, notice each person has an estimated risk of a little bit more than 2%. You have 10,000 people, each with a risk of a little bit more than 2%. How many deaths would you expect? You'd expect out of the 10,000 people, a certain number which can be calculated by multiplying that by the 0.0222. Well, the next slide will show you the result of that calculation. You'd expect 222 deaths if those 10,000 people were given the statin drug. Well, what if the 10,000 people were given the placebo drug, not given the statin? Now how many would you expect? Well, if I go back to the original table, remember 2.7% of them are expected to die. So what I could do is I could take those 10,000 people and multiply it by 0.27, whatever it was in the previous slide, and the calculation would come up that 277 were expected to die. That's what we'd anticipate based on Dr. Ridker's result. Well, we could take this calculation a bit further. We could say the implications of giving these 10,000 people the statin versus not giving them the statin is that if you didn't receive the statin, 277 of them would die, whereas the statin led to less deaths. It prevented deaths. Only 222 of them died. So how many lives would be saved by giving them the statin? It would be a difference of 277, or 55 people. 55 less deaths would be observed among those 10,000 people. That's a way to measure the effect of that drug on the outcome of mortality. Well, I could take it a step further. If 55 people are being saved, essentially, if you treat 10,000, I could say how many would be treated if I treated only 1,000? Well, 5.5 deaths. How many would be saved if I treated just 500 people? Well, what I could do is take this equation and let's divide the 55 by the number 55, and also to divide the 10,000 by the number 55. And this bottom statement tells me that one death would be saved, prevented, by treating 10,000 people divided by 55. Turns out to be by treating 181 or 182 people. That notion of saving one life, preventing one case of outcome by treating 181.8 people gives the foundation for what we call the number needed to treat. We would need to treat 181.8 people to prevent one case of the outcome occurring. So the concept of number needed to treat is how many people are treated with the drug to prevent one case of disease. And in this case, the answer is 181. Well, we can develop a formula. I've just said that 181 people are needed to be treated to prevent one case of the outcome, one case of death. Well, this 181 mathematically can be calculated by taking the risk of death in the placebo group, subtracting from it the risk of death in the treated group, and then dividing that quantity into the number 1. This is the formula for the number needed to treat. It's essentially 1 over a risk difference. It's 1 over the risk of developing the outcome in the placebo group minus the risk of developing outcome in the treated group. And if you go through the math, you end up getting the same value, 181.1. So this number needed to treat is a function of something we've described already, a risk difference. It's a alternative way to display the association between a risk factor, in this case a treatment, and an outcome, and maybe a more clinically appropriate way. But realize all it is just a variation of what we talked about before. It's 1 over a risk difference. And that goes back to what I said a few lectures ago. This is basically all we epidemiologists do to measure associations between risk factors and outcomes is take ratios or differences in outcome measures. And the number needed to treat is one of those examples. Okay, there's one other example I want to give you, and that I'll explain next time we meet. I want to talk about regression coefficients. So I'll see you next time.